All right, so now we're moving into Chapter 4, and in Chapter 4 we're going to deal with DC circuits, that is direct current circuits. This is in contrast to alternating current circuits, which are like what we have, the type of electricity that we have in our homes. But much of what we do here will also apply to AC circuits or alternating current circuits. So first, electromotive force, and we've already used electromotive force, but we just haven't called this. So it's really just a new word that we're going to use for potential difference. A battery or a power supply is a source of electromotive force. We call this EMF for short. And as I said, it's really just another word for voltage, though we'll make a slight distinction between EMF and voltage of a battery shortly. We'll use this symbol for EMF, script E or epsilon. As I said, it's going to be very similar to voltage, but when we talk about batteries, we'll see that batteries have an internal resistance. So batteries and power supplies have an internal resistance that we haven't considered as of yet. We've always assumed that a battery or a source of power, a source of electricity, is an ideal source and it has no resistance of its own. That is that it doesn't resist the flow of electricity at all. But that's not true even for the best of batteries. They all have some amount of internal resistance. And this internal resistance causes a drop in potential as the electrons move across the battery. So the electrons actually lose energy when they go through the battery. I mean, they gain more energy than they lose, of course, but they do lose a small amount of energy due to that internal resistance. So if we were to look at a battery, this is just a cartoon version. So, you know, this is the outer case of the battery and the positive and the negative terminals. The schematic of the battery on the inside will be a source of EMF. Right? That's the electromotive force, and that's the, you know, sort of the theoretical voltage of the battery, plus this internal resistance. And with those paired, that is the positive potential difference you get across the EMF source, and the negative potential difference you get across the internal resistance will combine to give you the total potential difference that you actually get from the battery. So in this battery, the terminal voltage, that is what you read if you were to stick a voltmeter onto the leads of the battery, the terminal voltage, which is delta V as I've drawn it here, would equal to the EMF minus I times R. Of course, this just comes from Ohm's law. It's the current times the internal resistance. So you can see that if you have a large internal resistance, as you do with batteries that are beginning to fail, then you'll get hardly any voltage at all because you'll lose so much potential difference in that internal resistance. And so as I said, so far we've assumed that the internal resistance is 0. That's never the case. And it's also because of this internal resistance, as I said, especially as they begin to go bad, that that internal resistance will actually increase, and you'll begin to feel that the batteries are warm with use, or maybe even very hot with use, because you have a large internal resistance, and then you have current going through that, and it sort of acts like a heater to heat up the battery. All right, so let's try this quick test on your own. You can find this. Now let's consider this circuit. In this circuit, we will